One of the more popular options for SignalVu for the real-time spectrum analyzers and oscilloscopes is the settling time option. In this video, we'll take a look at how to set it up and optimize it to get the highest resolution results. This video is recorded using a RSA 306B, the least expensive real-time USB-based spectrum analyzer. But similar results can be obtained with any of the other real-time spectrum analyzers, as well as with SignalVu running on the mixed signal oscilloscopes. Let's start by tuning in to where our frequency hopping signal is happening, and that's at 2.4453 gigahertz. When we take a look at this, we can see that the signal is hopping between one of three different frequencies. We can get a better view of this by looking at the real-time spectrum display, or the DPX display. This is only available on the real-time spectrum analyzers and not on the oscilloscope platform. We can see from this display that the signal is hopping between one of three different frequencies, here, here, and here. And we can also see that there is some overshoot and undershoot when it's tuning between these three separate frequencies. So let's set up an acquisition to acquire the transitions that are happening here, and then we'll dig into making the settling time measurements. We'll start by opening a display called Time Overview to acquire the data that we want. Let's also add a frequency versus time plot, which is the FMD mod. We'll be able to visually see the frequency changes of our signals. So with these displays open, the first thing we'll do is set up a trigger. And let's set up a trigger to trigger on the external input. The external input that I have is synchronized to this frequency hopping pattern. So I know that the pattern takes about 20 milliseconds to go through its entire sequence. So I'll dial in a 20 millisecond acquisition length and auto scale my frequency versus time plot. So now on this frequency versus time plot, I can actually see the three separate frequencies we're going to. The center here along the center axis is our 2.4453 gigahertz frequency. We can see we go from a low frequency to basically at center frequency, and then hopping again to a higher frequency, and then hops down to a lower one again and repeats. I'm going to adjust where I'm doing the analysis so I get a little more pre-trigger information, so I can kind of see where the sequence starts here. So now we can actually see the entire sequence here beginning to end. Now what we'll focus on is just this first transition from the highest frequency down to the lowest, because this is resulting in the largest amount of overshoot and ringing in the frequency transition process. So in order to do that, I'm just going to reduce the amount of time that we're analyzing here in our time overview display, and just focus on this negative going frequency transition. Now the frequency settling time measurement is essentially going to give us a display that looks very similar to frequency versus time. We go into displays, under RF measurements, let's add the settling time measurement in here, and I'll again auto scale that display. We can see the same frequency versus time characteristic in this display here as well. The pink vertical line here indicates where the measurement ends, and we use this to determine our final settled frequency. Obviously, this is not where we want this to be, so I can either adjust it through the settings or simply drag it with my mouse and say, okay, I want the end of that measurement to appear here, okay? And at that point is where we're going to assume that we're settled in our frequency at that point. And now we can actually see a couple of different measurements being made. You'll see two arrowed lines here, and one of them is measuring the settling time from when the frequency actually changes from its initial value, and then measuring how long it takes to settle after that. And the other one, as you can see here, says from trigger, is measuring from our trigger signal to where it settles to within precision here. You see these two blue horizontal lines, those are our lines of precision, of how tight we actually want to make that measurement, settle to within plus or minus some frequency. In fact, I'm going to get rid of the frequency versus time plot. We don't really need that right now. I'm also going to get rid of the DPX display. That'll help make this frequency settling time display a little bit larger. Let's open up the settings panel for the frequency settling time. And And I can see that I'm actually measuring to a tolerance of plus or minus 500 kilohertz. That's these blue lines that are right here. We could also see that I really can't make that any lower than that because I've got too much noise on that waveform to be able to get any more precise than 500 kilohertz. Now, the purpose of this video really is to show how we can get much, much better and much tighter tolerance in this measurement result. So let's take a look at the things we can optimize. The very first thing we want to do is optimize the reference level for the signal. With any spectrum analyzer, you get better signal to noise ratio the closer the signal is to the reference level. So in our case, I can start reducing this reference level to get that signal closer and closer to the top of the screen. And as I start reducing this reference level down, so I get to about -6, -7 dBm or so, we would see the signal to noise ratio here has improved quite a bit. In fact, to the point where I can get down to about a 250 kilohertz tolerance and still get a reasonable measurement. I can't get too much better than that, but I've been able to optimize that a little bit. I'm going to just pan this time overview display down here a little bit so I can kind of see a little bit what's happening here. And again, just using a marker, I really want to make measurement of how long it takes to settle out into this region right here where the marker is. So the next thing we can do to optimize this frequency settling is to recognize that currently under our settings here, we're using a 40 megahertz acquisition or measurement bandwidth, and that's much more than we need. In fact, we can make this measurement with about 10 megahertz of measurement bandwidth. So if I reduce the measurement bandwidth from 40 meg down to 10 megahertz, we can see we've tightened up that trace some more. We've gotten a little bit better signal to noise ratio, which is now going to allow me to bring my plus or minus tolerance down to about 100 kilohertz. So we've made a 5x improvement so far from 500 kilohertz down to 100 kilohertz in terms of how precise we can actually make that particular measurement. Another technique that we can use to further smooth out this trace to get a finer tolerance is to apply some smoothing to the waveform. There's a lot more points in this waveform than we actually need. The smoothing allows you to essentially set up boxcar averaging across the waveform. And this can be increased all the way up to 1,000 points. And we can see if I smooth that out by 1,000 points, it hasn't really changed the shape of this waveform. So I know I haven't really altered the result. But now I've gotten this trace to be much finer. And in order to see how fine I've gotten, let's actually vertically zoom into this waveform to see what's going on. So I'm just going to right-click and select zoom and just zoom this waveform up vertically. So I can actually see how much cleaner that waveform has gotten. And now I can get down to much lower in terms of the frequency settling measurement that I can do. So now I'm down to plus or minus 5 kilohertz. So I've improved by a factor of 100 from our initial tolerance of 500 kilohertz down to just 5 kilohertz. Now in our case, we're actually looking at a repetitive waveform. And because we're repetitive, we can take advantage of averaging to smooth out the noise even further. So if I go back under my traces tab, let's put some averaging in here. Let's employ an averaging of, say, 10 averages over time. So now I've taken out any of the uncorrelated noise in this frequency versus time plot. And now I can actually bring this tolerance down even further. So to the point where I can even measure to within 1 kilohertz of final settled frequency. So we've made an improvement of about 500x from our original 500 kilohertz tolerance down to 1 kilohertz tolerance just by appropriately setting things like reference level, some trace smoothing, and some averaging. To go further than this, we can reduce the measurement bandwidth even further. But now what's going to happen as we do this is we may reduce that measurement bandwidth to the point where the initial frequency that we started from will be outside of the measurement bandwidth. So it's helpful to note at this point where what we've got in terms of a difference between the triggered settling time measurement versus the settling time from where the frequency starts. And if we take a look at this, we're typically about 30 microseconds difference between the two. Because once we reduce the measurement bandwidth to exclude the initial starting frequency, we won't get that first settling time measurement anymore. So as long as we know it's about a 30 microsecond difference, we can continue to make the measurement just from the trigger. But now if we reduce this measurement bandwidth further, what we really want to do is center the measurement frequency on the final measured frequency. So one thing I'm going to do for that is take a look at the spectrum here, and I'm going to reduce the spectrum, the RBW of this spectrum down to say 2 kilohertz. I'm going to move my spectrum measurement time over to about where my marker is, because I know that's where I've settled out in frequency. And I'll take that marker and put it on the peak and see that my final settled frequency is basically 2.4422 gigahertz. So I go back to our settling time. In fact, I'll maximize this display and set the measurement frequency to 2.4422 gigahertz. I'm going to set the position back to 0 because I want that to be at that 2.44. And it looks like we're probably a little bit low. I might have to make this, maybe I'll make this 2.44222 gig. And that centers us up pretty well. So now that I've established that new measurement frequency to be right in the center, I can now reduce this measurement bandwidth even further. So if I go down to even a 1 megahertz measurement bandwidth, now I can actually bring this tolerance down as tight as about 100 hertz. In fact, let's zoom in on this even further. Okay, I'll pan this up a little bit. Okay, and we can see now there's a plus or minus 100 hertz tolerance, and we're measuring that settled frequency to within plus or minus 100 hertz of that settled time. And we can see that it's taking 1.73 milliseconds from the trigger to get there. And we also know from our previous result that we're about 30 microseconds longer than that to go from our starting frequency. So with these couple of changes, we've actually made a 5,000x improvement in our settling time resolution by optimizing the measurement within frequency settling. So now in some cases, you may also have some requirements for what the ringing does and what that ringing looks like while you're settling or even before you've settled out. So I'm going to store up to a little bit wider kind of result here like we had earlier and show you how you can actually employ some mask testing to do some of those measurements. So let's go and auto scale this result again. And now I can actually see my complete settling time again. And if we go to our mask settings, we can enable the mask test, and we basically have 3 different vertices we can set up. Let's start off by setting the first one to be, say, 100 microseconds after the trigger, and set up that limit to be, say, plus or minus 4 megahertz. All right. And the next one, let's set that one to be, say, 250 microseconds after the trigger, and set that limit to be, let's do 2 megahertz on that one. And then we'll take this final one here and set that to, say, 500 microseconds after the trigger, and leave that tolerance there at 500K. So you can set up these masks to ensure that the transition also meets specific timing criteria, as well as making the measurement of how long it takes it to settle out to final frequency. So the settling time option can be used for measuring frequency hopping and frequency tuning of things like synthesizers and PLLs, and can be used to measure not only how long it takes for the signal to settle to final frequency within some tolerance, but there's also a display that will show you how long it takes to settle to final phase. These same optimization steps that we followed here are applicable to that measurement as well. And they're also applicable whether you're using a real-time spectrum analyzer or an oscilloscope that's running SignalVu to make this measurement.